Okay, with our next one here, this one I've written the reagents out, and hopefully you can recognize those reagents. This is oxyl chloride. This is the Swern reagent. DMSO is a solvent. When we do a Swern, we will use a weak base to finish it up. So we have a weak base in a separate step. But this entire thing together is just the Swern reaction. So, hopefully you can recognize the reagents. Now, I may, on your exam, just write Swern, or I may write the reagents out. You need to be able to recognize them. Like we had back here where you had to give the reagents, I told you you can just say Swern. You don't have to write them out. But I may write them out, and you have to recognize, okay, that's Swern, or that's PCC. You know, I could draw those out like I did here. Okay, so anyway, this is all together. This is just the Swern reaction. So Swern is an oxidation. Now, we have a ketone up here at the top. Let's just examine what we have. We have a ketone. You can't oxidize a ketone any further. That's as far as you can oxidize that carbon. We have a secondary alcohol. Now, you can oxidize a secondary alcohol, and we have a primary alcohol that can be oxidized as well. But the ketone cannot be oxidized, so that ketone stays the same. Secondary alcohols, we had one here just a moment ago. Secondary gets oxidized to a ketone, so this becomes a ketone. Primary alcohols can get oxidized to an aldehyde, or they can get further oxidized to a carboxylic acid. Swern will stop at the aldehyde. PCC or Swern stops at the aldehyde. Chromic acid, potassium permanganate, all of those took it on further to the carboxylic acid. So this carbon here is going to become an aldehyde. And you don't change the number of carbons. Make certain you got the number of carbons. I did have a carbon right here hanging off. I still have that same carbon. We don't change the number of carbons with an oxidation or reduction. Okay, so there's our product with the oxidation. That primary went to the aldehyde and stopped at the aldehyde. Secondary alcohol went to ketone. That's all you can do with the secondary. Questions? Okay, our next one here, let's see what we've got. First step, I have a Grignard reagent. Grignard, you know there's partial positive on the metal, partial negative on the carbon attached to the metal. Our carbonyl over here, there's partial positive on the carbonyl, carbon, partial negative on the oxygen. So it's this carbon that's attached to the magnesium. This is coming and attacking the carbonyl, and we kick the electrons up onto the oxygen. Two lone pairs, now there's three lone pairs if you want to show that. Let's see, we got 1, 2, 3, 4 carbons there, so got to have 4 carbons hanging off. Okay, there we go. So there's our product after the first step. Just check, anytime you kick up onto the oxygen, check and see, can they kick back in and reform the carbonyl if you have something you can kick off, and we don't. It's carbon-hydrogen bond, you're not going to break it. Carbon-hydrogen, nope, and carbon-carbon, no. So it's stuck here. Last step I'm adding in, we're adding in chromic acid, and we have water. Well, chromic acid, that's an acid, water is an acid. That's going to protonate the oxygen. So you can, if you want to show mechanism, you can show it going to the acid, or you can show it going to the water, either one. It's picking up a proton. So it becomes an alcohol. chromic acid is an oxidant. So I protonated and got an alcohol, but chromic acid is an oxidant, so it oxidizes that alcohol. And it will oxidize it all the way. Chromic acid oxidizes the primary alcohol, oxidizes the primary all the way to a carboxylic acid. So that carbon right there becomes a carboxylic acid. And there's your product. Questions on that? So that one was a little tricky because you had added the Grignard, and then I had an acid protonate, but then that acid is also an oxidant. It's one of the chromium oxidants that we had, and goes on. Yes?
If it had just been like hydrochloric acid, would it have stopped?
Yeah, you would just, hydrochloric, you just protonate and stop.
Okay.
Or like the ammonium chloride that we had, you would protonate and stop. Or if I just had water only, we protonated and we would stop. But because it's the chromium one, that chromic acid, we know that's a strong oxidant. Other questions? Okay, next one here. Let's take a look at this one. First step, we are adding in magnesium metal. I have an alkyl halide. Magnesium metal, alkyl halide will make the Grignard. So this one becomes a Grignard reagent. That magnesium inserts in between the halogen and the carbon. But it says there's an excess magnesium. So the same thing will happen with the other alkyl halide. This one also becomes a Grignard. So I have a di-Grignard. You got a Grignard on both ends. Okay, so there's our product after the first step. Any questions on the first step? Yes?
Will we have a first step like that on the exam since you said we won't be synthesizing Grignards?
No, I said we would. I said I wouldn't ask the mechanism for the synthesis of a Grignard.
Thank you. Perfect.
Or the organolithium. I will not ask that mechanism on how it works. Because that went through, we had a single electron transfer and all that type of stuff. You dealt with the radical and everything. I said I would not ask that mechanism, but I do expect you to know the reaction. So yes, I will ask the reaction, but I will not ask the mechanism.
Would Jones' reagent be included in that?
Jones did not have a mechanism. We did not, there was none of the oxidations we covered a mechanism on. We didn't cover a mechanism on any of the oxidation reactions. So I will not ask a mechanism there either. So it'd just be mechanisms that we covered, but the only one that I can think of that we covered, that I covered a mechanism that I said I would not ask was to make a Grignard or to make an organolithium. I said I would not ask that mechanism on my mechanism question. So I always have, there on first page, I had one mechanism question. Now here, you don't have to show a mechanism, but if you want to, you can. It won't hurt anything. You can show the mechanism, but you don't have to. All I'm asking is the major product. All you have to do is show the final product at the very end. But I would kind of draw out at least after each step so that, if you mess up somewhere along the way, I can at least give you credit for getting to here, and then if you mess up on further, I can count off for that, but that way you don't lose all the points. Okay, so let's see what we do here in the second step. So we're reacting with this molecule. We know what a Grignard will do. Grignards like to attack the carbonyl carbon because there's partial negative on that carbon, partial positive on the metal. Same thing on the other one, no matter which end you use. So this is going to attack, keep the electrons up onto the oxygen. Now, I use this end, so this carbon here, that's this one here. Let me just highlight it. I'll say CH2 right there, and that's this CH2 right there. That's the one that attacked. Now, anytime we attack and kick the electrons up on the oxygen, we always need to look and see, can they kick back in and reform the carbonyl if we have a leaving group, and we do. So I made the carbonyl back. But, wait a minute, I'm missing the carbon. I misdrew. Oh, I missed it over here. 1, 2, 3, 4. 1, 2, 3. Yep, right there. I'm missing a carbon there. Sorry. Can't count. One, 2, 3, 4. Okay, that's right. Now, I have a carbonyl that we've remade, and there's also still a Grignard down here on the other end. We used one Grignard here on one end, but I've still got the Grignard back here. It's still on there. Got a carbonyl, got a Grignard. You know what happens. The Grignard reacts with a carbonyl. So this one is also going to react with the carbonyl, and we'll kick the electrons up onto the oxygen. So it closes up and makes a ring. See, it came up and attacked that carbon, kicked the electrons up on the oxygen, so it made a ring right there. Because I had the Grignard on one end, I had the carbonyl here on the other end, and so it just closes up, makes a ring. Now, if the electrons try to kick back in and reform the carbonyl, it can't. There's nothing, we don't have a leaving group, so it's stuck here until the last step. We add in acid. And this simply picks up a proton off of the acid, and that gives us our alcohol. There's the final product. Questions on that? That was a little bit tricky. You had to kind of work through it. That one rules out the people that try to memorize everything. I like a question like that. Those who memorize everything, they would have no idea what to write there. But the people that know how to work through something can figure that one out. So molecules can react with themselves like they did here. This is actually really, really fast. Molecules react if they can, they got somewhere to react at, they will react with themselves much faster than reacting with something else. Because it doesn't have to go find something else. Now, let's say Ethan and I both have an itch on our back. Our back is itchy. It's easier for me to reach around and scratch my own back than go over there and try to scratch his back for him. You know, it's faster just to reach around. That's what happened here. It just kind of reached around and scratched its own back. It didn't have to go find something else to react with. So those are really fast reactions when something can react with themselves. Let me give you another example of something reacting with itself. I didn't do this in lecture, but I'm going to just add this in as a bonus here. Diels alder sometimes work with themselves. Try to think of something here. I'm trying to. Figure out how to get this attached. Here. There we go. That'll work. Do this one. You take that molecule and just heat it. All you gotta do is heat it. And right here we have a diene. And right here I have a dienophyl. And those can react with one another. Now those are separate because they're not conjugated. The diene counts together because these are conjugated. And this is a separate, the dienophyl is separate because it's not conjugated to that, so it is separate, but they can come together and react. And we do the same reaction like we do on a regular Diels alder. So I'm forming a single bond across here, and forming a single bond across here, playing a double bond there. There's the product. And that works very well. This is, I mentioned that Diels alder is often used to make your pharmaceutical drugs and steroids and things like that. A steroid has, I don't remember exactly how it is, but it's got 4 rings together. A steroid does. Can't remember exactly what the exact shape of a steroid. I can't remember, but it's a steroid is like 4 rings, something like that, and then they got different things coming off. But steroids all have 4 rings, and that's one of the things that happens. You got several Diels alder that start building together. So, this is very fast to react with itself. So you can have something reacting with itself to do a Diels alder, just like we did the green yard there. Okay, a little bonus there. Let's see, where are we at? Okay. Holy cow, 4-step reaction? Dr. Selby, what are you doing to us? Don't freak out, just go stepwise. Yeah, I combined several things into one problem here, but let's just go stepwise. First step, we're adding HBr, and the big thing to notice is that it is at 40 degrees. We talked about controlling, doing the thermodynamic and the kinetic. We had 40 degrees and minus 80. You get the thermodynamic at 40 degrees, you get the kinetic product at minus 80. The kinetic was the 1,2 addition, thermodynamic was the 1,4 addition. So, at the 40 degrees, we're going to get 1,4 addition here of HBr to a diene. Now, where are you going to add it? Well, you don't add to a phenylrene. We haven't dealt with adding things to phenylrenes. Here is the diene that we're going to react with. There's the diene on this side. So I'm adding HBr. Now, HBr is strong acid. You look for something protonate. We're going to protonate one of those double bonds. It does not matter which one you go to. The molecule is symmetrical. It does not matter. So one of these gets protonated. We're going to get the proton and we'll kick the bromine off. Now one of those two carbons gets the hydrogen and one's going to get a plus charge because initial tail becomes more positive charge. So do I want the plus charge here? Do I want the plus charge here? We want it here because that's one, it's tertiary, plus it's also allylic. It's got resonance with the double bond. So that CH2 here becomes a CH3. There's where the hydrogen went. Now we have the bromine. If I add the bromine now, that's 1,2 addition. We said we need to do 1,4. There's 1, 2, 3, 4. I add the bromine right now, that's 1,2. That would happen if you're at minus 80. But at 40, this is going to do resonance next. At the 40 degrees, we do the resonance and then add the bromine. So the electrons kick in, form the double bond there, and that leaves the plus charge there. Now the bromine's going to add. That's our 1,4 addition. There's our product after the first step. Second step, I'm reacting with lithium. And it is 2. We had to use 2 lithiums to put 1 on. So the lithium adds on to where the halogen is. It replaces the halogen, if you recall. So we make the organolithium. There's our product. The other lithium went to make lithium bromide. That's why we had to have 2. One makes the organolithium, the other one makes lithium bromide salt. But here's our organic compound. So there's our product after the second step. We have the organolithium. Now we're going to react in the third step. I'm reacting with the carbonyl. So we know that organolithium, this carbon attached to the lithium, this carbon will attack the carbonyl and kick the electrons up onto the oxygen. There's our product after the third step. Fourth step, we're adding in acid. By the way, there's nothing else this can do. If the electrons try to kick back in to reform the carbonyl, there's nothing we can kick off. Always check for that, but there's nothing we can kick off. So it's stuck there until we add in the acid in the fourth step, and then this just simply gets a proton off the acid, and then we have our product. We have an alcohol as our product. There's our final product. That's all I care about. But like I said, it's often wise to at least work through some of it so that if you make a mistake, you know, if you just messed up here, I can at least give you credit for getting to there. Try to write out a little bit. Questions?
Is the E2O, is that just the solvent?
Yes, diethyl ether. That's diethyl ether. Yeah, that's just the solvent. We always use the diethyl ether as the solvent for the green yard or the organolithium. you will always see that diether as the salt. Because I mentioned that's a solvent that we can get nice and dry. We can get rid of all the water out of it. You can actually buy bottles of anhydrous diethyl ether, which anhydrous means it's dry. It means there's no water in it. And you can, a chemist, we can order those, or you can dry them yourself. And we will order those. And so next week when we do the green yard in lab next week, I will have anhydrous diethyl ether out there that you will be doing the reaction in. So again, here we've got diethyl ether again, just the solvent. But I have lithium aluminum hydride that I'm reacting in the first step. So let's see what we have. Lithium aluminum hydride, full plus charge on that lithium, full negative on the aluminum. And it likes to lose a hydride. We like to transfer a hydride. Now hydrides are very strong bases and I happen to have an acidic proton. So acid base would actually happen first. This would come and get the acidic proton, and we'd be left with, if you'll allow me just to take that off and make an anion. So technically, that's what happens first, is we come and get that and make an anion right there. But remember, lithium aluminum hydride can transfer all 4 of its hydrides. It can transfer all 4 of those. So then you get one, got plenty. Now the next one can come in and attack the carbonyl. We'll pick up the proton back here when we add in water in the last step. That's when we'll get a proton back. But we've attacked that carbonyl, brought in a hydride. I'll just go ahead and draw the hydrogen on there. So we brought in that hydride, so there's a hydrogen on there now. Anytime you kick electrons up onto the oxygen, look and see, can they kick back in and reform the carbonyl if you have a leaving group? And we do. We're going to kick off this oxygen. So that gives us an aldehyde. Now remember, you can transfer all 4 hydrides on the lithium aluminum hydride. We've used 2 so far, but I can still do another one because you can transfer all 4. We're going to go again. I'm just going to say LAH right here. Lithium aluminum hydride. That makes it easier for me to draw. So we're transferring another one. Now if the electrons try to kick back in, reform the carbonyl, there's nothing we can kick off. So it's stuck there. Nothing it can do until last step we add in water or any other acid. Water is an acid, can serve as an acid. Just need some acid to protonate, and you're going to add plenty to protonate everything. So both of these are going to pick up protons, and we're left with alcohols there. So there's our product. So that ester got reduced all the way down to an alcohol. The alcohol stayed an alcohol, but it was involved there. It did get to react technically.
So
you wouldn't have to show that. I wouldn't care, but technically it did.
So the lithium aluminum hydride, the reason why it can keep on going down is because it has so many hydrogens.
It can do all 4 of them. So I showed you in lecture how it does all 4, but it can do all 4. Because it winds up you get an oxygen that adds back to it. After it transfers one, then an oxygen will add back to it. And so then that gives it a negative charge again, so we can transfer another one. And then when you do that, you add another oxygen back to it and gets another negative charge back. It just keeps going until all four are gone. Yes?
How come the H didn't take at the other oxygen right there? We made it just go straight to the carbonyl carbon. Is it just
Here?
Yeah, right there. That one up there. Up there with the negative, the oxygen up there. How come that oxygen didn't
Oh, wow,
attack
that
here?
one didn't attack?
Yeah.
Even if it did,
Mm-hmm.
let me just show you. That's a good question. That's a good question. Let me just take this off. So this doesn't happen, okay? So I just want to show you why it doesn't happen, is what she's asking. If that did happen, and we attack and kick up, this is what you get. And it's got a couple things that's some problems. One, it's a 4-membered ring that it made. 4-membered rings aren't very stable. They're pretty unstable. But more importantly, is anytime you kick electrons up on the oxygen, look and see, can they kick back in, reform the carbonyl if we have a leaving group? Carbon-hydrogen bond? No. Carbon-carbon bond? No. Carbon-oxygen bond? Yes. So it comes right back off and goes right back here.
Oh, okay.
It just went right back. So even if it did add, it's going to break back apart and go right back to where you started. Because it's got a leaving group.
How do you know when to use like water versus hydronium? Just like not this reaction.
It doesn't matter.
Okay.
It didn't matter. I could put hydronium here. Nothing wrong with that. You just need an acid.
Okay, so they'll always be interchangeable.
Yeah.
As far as this example.
I can use any acid here. I could use HCl. I could put sulfuric acid. I could put, we had the ammonium chloride. It does not matter what it is. We just need a proton source. We need some acid to serve as a proton. And water is an acid. It's pretty weak. These are a lot stronger. But water can serve as a proton source.
Okay, thank you.
So, yeah, nothing special about that. Just need some acid to protonate them so that we can get the hydrogens on there. So yes, sometimes, that was a good point. Probably should have pointed that out. Sometimes I write a hydronium, sometimes I write water, sometimes I write ammonium chloride. You just never know what I'm going to write there, but it didn't matter. You just need a proton. You need some acid. That was another good question. Y'all got some good ones if you just ask them. You don't ask many, but you ask good ones when you do ask. Okay, our next one. First step, I have TBS chloride. That is our protecting group, if you recall. This TBS is a protecting group. Imidazole is a weak base to help get rid of the hydrogen off the alcohol, but this is going to protect the alcohol. That's putting a protecting group on. So it's the alcohol that attacks that's a silicone atom, even though it's just an S there. We abbreviated TBS. That's tetrabutyl dimethyl silyl chloride was actually what it is, and it kicks the chlorine off. But we put a TBS group on there. The imidazole gets the hydrogen. So that oxygen has become we put a TBS onto that oxygen. That's a protecting group. So now there is not an acidic hydrogen present. Second step, I react with the Grignard. So the Grignard will react with the carbonyl now. And kick the electrons up on the oxygen. If I had not protected that, the Grignard would have been destroyed by the acidic hydrogen. Now we talked about two ways to get around that problem. One way is to put a protecting group on, and that's what this problem had. The other way, the easier way, is just to react with two equivalents of Grignard. Yes, one of them is wasted on the acidic hydrogen, but then the second one can react with the carbonyl. So I'll waste one, but then the second one can react. So you can use two equivalents of the Grignard, or you can do a protecting group. Now the reason I say two equivalents is better, because it's easier. You just add in extra, and it doesn't add a step. This protecting group, that's adding a step. I have to put the protecting group on, and then I got to take it off at the end. It's just adding more work to us in the lab. But that's what this person did here. That's what's on the test here. So let's see what we come up with. So we put the ethyl group on. Ethyl attacked the carbonyl, kicked electrons up on the oxygen. Now, if they try to kick back in, reform the carbonyl, there's nothing we can kick off, so it's stuck here. The last step, we are adding HF. So we talked about that the fluoride ion, fluorides like to remove, they love that TBS group. So the fluoride's going to take that off and kick the oxygen off. But then we've also, HF is an acid as well, it's got a proton, so it's going to protonate both of those as well. So both of those wind up becoming an OH. It takes the protecting group off and it protonates those oxygens. And there's our final product. So we get the alcohol back on this one, and we've made the new alcohol down here. So HF, fluorides, remove protecting groups, and then it being an acid protonates those as well. Questions? Okay, our last one. So, like I said, a much easier way to have done this that would have saved you some time instead of doing all this. If you had just done the first step, done two equivalents of Grignard, and then in the second step, just use any acid, we would have got the same product, and it only took 2 steps instead of 3 steps. 2 steps is always better than 3 steps. You get out of the lab quicker, right? That's what you all want. Get out of the lab as fast as possible. I know how you are. I'm the same way. I like to get out earlier. Okay, this one here, let's examine what we have here. Let's see, I see a primary alcohol. We have a tertiary alcohol. And we have a ketone. Okay, now, I have a very strong oxidant. This is one of our strongest oxidants. So we can oxidize. Chromic acid and water will oxidize a primary alcohol all the way to a carboxylic acid. So that carbon becomes a carboxylic acid. You don't change the number of carbons. So it's this carbon that I'm highlighting right there, that carbon becomes a carboxylic acid carbon. That became a carboxylic acid. I did not change the number of carbons. Now, a tertiary alcohol cannot be oxidized. Remember, we can't oxidize those. If you try to oxidize it, it would be breaking the octet rule. You know, I'll just show it here real quick. If I were to make that a carbonyl, look, I've broken the octet rule. I've got 10 electrons around that carbon. That's not possible. So you cannot oxidize a tertiary alcohol. It has to stay. A ketone cannot be oxidized any further. The only carbonyl that we talked about that can be oxidized more is an aldehyde. You can oxidize an aldehyde onto a carboxylic acid. Because that's what happened here. The primary alcohol first goes to an aldehyde and then it goes on to a carboxylic acid. So if you were to have an aldehyde somewhere, it would go on as well. Because if I can't stop this at the aldehyde, then if you have an aldehyde present, you can't stop it either. It's going to get oxidized. So there's our product. We've done an oxidation and oxidized all that we could. The only thing that this one had that we could oxidize was the primary alcohol. So we talked about that tertiary alcohols, you cannot oxidize those. We also said you cannot oxidize a phenol. Don't forget that. This will not oxidize. That's a phenol, an OH on a phenyl ring. You cannot oxidize that alcohol. It will always stay a phenol. So it's not possible to oxidize that. We've talked about other oxidations that would have went all the way to the carboxylic acid. So chromic acid was one. We also said you could make the chromic acid. Remember that was chromium trioxide and sulfuric acid. And this would be done in water. This was called the Jones reagent. So this just makes chromic acid. So this will do the same thing. And then we also talked about potassium permanganate. Potassium permanganate was another very strong oxidant. So all of these would work. Chromic acid or Jones or potassium permanganate. So we talked about all of those. If you use the potassium permanganate, you got to have a separate step where you acidify. Because potassium permanganate, you always use a base with it, and so you need an acid to neutralize. That's the only difference. But any of those would have worked here. Okay, so that's the old exam. Now, any questions you got about anything, homework, problems, or anything, I'll be happy to help you with those. Anybody got anything else? If you don't, that's all I got. Get out and go. I hope that